All right. Thank you, Susan. And thank you guys for coming out. How many people made it to the Microservices Day we had about a year and a half ago? Just a couple. Oh, all new people. Cool. So we're going to be talking about microservices. I assume people have heard about microservices. We've been talking about this topic for about 3 years now. How many people believe they're doing microservices in their environment today? Raise your hand high. Come on, people. Let's get some energy. Just a couple. How many people have been told that they're going to do microservices? All right. We're gonna be looking at it from a few different aspects today. The topic that I'm going to look at is what are the emerging trends in the industry today? Where did we come from, and what are some of the emerging trends? It's not going to be an intro to microservices as much as it is, hey, pay attention to, this stuff is moving fast, pay attention to what's happening in the community today. My name is Christian. I'm a chief architect or senior principal architect at Red Hat. I travel all over the United States, and I help our Red Hat customers understand what microservices is, how to implement it, what it means for them, what DevOps, why we need DevOps, why we need automation, why we need the infrastructure in place to make this happen, and of course, touch on maybe the less tangible parts, the organizational parts, the cultural parts, and so on. I did spend a bit of time at Zappos.com, and I got to work closely with some of the folks at Amazon. So this was now 5 or 6 years ago, and even then, I got to see how a mature automation and what we're calling microservices, what that architecture looks like internally, and I try to help bridge the gap between where enterprises are in their initial journey into what I saw of an organization that was 10 years well into their journey. I wrote a book, Microservices for Java Developers. We'll have a copy of it, a printed copy of it back there during lunch. I do a lot of architecture work, and I do a lot of speaking and blogging and all that stuff, but I feel like to have any pulse on the community and a pulse on viable solutions, you actually have to have your hands in the code. So I try to contribute to open source communities as much as I can. My background is in messaging, working on message brokers, things like Apache ActiveMQ. Has anybody heard of that? A couple? I've contributed a little bit to Apache Kafka. Anybody heard of that? I'm currently contributing to a project called Istio. Anybody heard of that? Oh, okay, good. A couple. All right. Go to developers.redhat.com. Lots of great content. Copy of my ebook. Ed Senyanago is going to be speaking next. Copy of his book on managing data and decentralizing data in a microservices environment. Other things on Vertex and .NET on Linux and all this. There's lots of great content here. Okay, so we're going to dive right into it because I don't have that much time. Microservices are an architectural approach to building our applications where we decentralize things and break them down into smaller pieces. Hopefully you've all seen different definitions, but the nasty part of it is these are distributed systems. Distributed, and everybody has a different definition for distributed system. For me, it's just components that are talking over the network. The problem is the network just does whatever it wants. It is completely just, anybody experience this firsthand, where the network just says, screw you, I'm doing what I want today? Nobody? Right, so you've heard of the fallacies of distributed computing, that the network is not reliable, it's not secure, it's not homogeneous, and so on and on and on. As we build services architectures that more and more become decentralized and have to communicate over the network, we're removing the complexity of what we would otherwise see in a single monolithic app or not have to deal with or be abstracted away from. We have to deal with this at the forefront. We have to deal with things like partial success. If I make a call over the network and I don't get a response, did it succeed? Or did it time out? Did the other side fail? Did it succeed and then fail? What we have to deal with and what we have to think about as the network changes, things like an elastic infrastructure where we have to find services at runtime, service discovery, adaptive load balancing, retries, timeouts, these types of basic things, that complexity gets moved in between our services. But we've built systems that talked over the network before. Now, in the past, I would argue we did a lot to make the network, make everything as failure tolerant as possible. We would say, well, my network doesn't have those issues. That's your network. But I would also argue in this move to the cloud, that's not the case anymore. There's a high uncertainty in how the network is going to behave. So how have we solved this in the past, though? How many people have seen an architecture where your applications use messaging in a more synchronous looking way? How many people have done request reply over messaging queues? Just a couple? Cool, good. Messaging, in my mind, is more of an asynchronous style backbone. But I would say that when we did this RPC style communication over message brokers, message queues, we were solving things like service discovery. Where's the consumer? I don't care, I put it on the queue. We were solving things like load balancing. Well, if these queues get real deep and I put a lot of tasks on there, well, I can just spray them over a bunch of consumers, competing consumers, right? Things like retries and timeouts, acknowledgements and NACs, poison messages and so on. These were built into the messaging protocol. And then we thought, well, if we have our traffic going over these message queues, and we're getting some of this networking behavior that we need in the application, then what if we added things like transformation and content-based routing? And we built this entire bus that was supposed to magically treat the applications as though they don't really have to really know where they are or anything about the network or any of this stuff, right? We could just ignore the fallacies. What we ended up doing is merging a lot of the business logic that you would need to perform these types of functions into a central location, into a central bus. And this proved to be beneficial in some ways. You could attempt to keep real good governance and change controls and so on. Alternatively, this strangled the ability to make changes. Now you have a bottleneck. Now you have a single location where, not just architecturally in the system, but as a team, as an organization, as a group of people. These are the integration people. These are the ESB people. That ends up becoming a bottleneck. But if we look at the way the major cloud vendors, the Amazons, the Facebooks, the Googles, and so on, they didn't go that approach. They didn't centralize it because they knew that if you try to run things in the cloud, the network's unpredictable. There's reduced certainty, there's uncertainty. What they did was they said, well, the applications will be autonomous. We'll build some of this functionality into the code, into the services themselves. They'll provide functionality like retries and circuit breaking. Have you heard of the circuit breaker pattern? Seems to, Michael Nygaard introduced it, and it's been around for much longer, but he made it more explicit in his book, Deploy It, or what was his book's name? That was in 2007. But that gets pretty closely aligned with, well, this is a microservice pattern. Well, it's a distributed systems pattern. Netflix came out with a bunch of different libraries and frameworks for doing this. Netflix, who's since become the poster child for the emergence of this microservices movement, they, back in 2007 or 2008, whenever they said they were all in on AWS, they went all in on AWS and had to build a lot of this platform themselves. They targeted Java workloads on VMs in AWS. Now, these are absolutely, and Netflix is awesome for open sourcing these things, because it made some of these patterns and this platform more accessible to a lot more people. The trouble is when you start to look at building services as discrete, autonomous individual components, individually deployable and so on, you will probably run into the fact that you'll also may want to implement certain components in a different programming language, or maybe a different framework. And as you start to figure out, well, okay, so if we standardize on Netflix OSS, Java-based, then if we use other Java-based tools, that should be okay. right? In Spring Cloud, anybody use Spring Cloud? Not that many? What? Spring Cloud Netflix is a derivative of the Netflix OSS libraries. But what if you're using Vertex? Have you heard of Vertex? We'll be talking about Vertex today. It's a reactive programming model that didn't originally fit very well with the Netflix OSS libraries. But what if you're using Node.js? Then do you go off and re-implement all of these libraries yourself? But what if you're using Go? Or whatever, right? Python, Perl. I've seen people write Perl, build services. But you get the point, right? So if your platform is so locked into a single language and potentially even single framework, you're excluding all of these options that you might want to keep open for your architecture. Even the author, the creator of some of these Netflix libraries, Ben Christensen, who I think is now at Facebook, he would argue that it's more important to have a standard protocol, standard API, or interface into the platform than it is you got to use this version of this language library and jam this into your code. So the things we need to solve for because of distributed systems, where we could see a proliferation potentially of these libraries. Things like service discovery, retries, timeouts, circuit breaking, load balancing. The ability to route. As traffic comes into the architecture, we might want to route it to certain clusters that might be living in certain clouds or on-prem or however. We want to shape the traffic. Doing health checking, we want to do, the ability to have controlled routing gives us the opportunity to do things like A/B testing, canary releases, much safer and lowering the risk of doing a release or a deployment. Logging, observability, understanding what's happening in the system. These are all potential areas where we could see a proliferation of a bunch of libraries. And as you start to bring all these libraries and these dependencies into your code, now your code, which is supposed to be focused on differentiating business logic, has to concern itself, which developers, we should absolutely be concerned with the network, but the actual implementation and where those implementations live as being commingled and integrated into your business logic, that has some drawbacks. These are all horizontal concerns. It doesn't matter what combination of framework or language, these are all horizontal concerns. Some of the drawbacks to doing this in the library form, you would need one for each combinatorial explosion of languages and frameworks that you have. You need to maintain and upgrade. These each have their own life cycle now. Well, if the Node.js one changes, do I have to change the Java one too? It increases the chances of these things being misapplied or being applied inconsistently or incorrectly. So now you have a system where you have this false sense of hope because you think, well, I have these circuit breakers in place, but they're not behaving exactly the same, or they're not behaving the way that you're expecting them to. What if we could do this? We're computer technologists. Well, that's a problem. Let's just abstract everything, right? We'll just build another layer of abstraction. But what if we just say, we're going to take this functionality. We don't want to abstract it away. You can't ignore it. But let's put it into a single binary, a single place that it doesn't matter if you're using Java or Python or Node.js or whatever. Right? We put it in a single place, and we can apply it consistently, and all the traffic would go through it. Now, you might be thinking, well, I don't want to force all of my network traffic through a single proxy. That sounds backwards, right? We're centralizing things again. Hold that thought. Has anybody heard of Envoy proxy? Cool. Envoy is a proxy that was written in C++, came out of Lyft, developed originally by Matt Klein and folks at Lyft, that is this binary that provides this functionality, these features. It is a network filter, so it processes bytes. You can write protocol, L7 level protocols on top of it, like HTTP. They have MongoDB and Cassandra and others I'm sure we've written. It supports HTTP2 out of the box, so you can do things like gRPC. It has advanced load balancing and statistics, and since the requests are going through the Envoy proxy, it understands when there are failures, it understands when there is latency and there are circuit breaking events, and so it has a lot of insight into what's going through the pipes that it's controlling. So this is that. So that's Envoy. Envoy is that binary that we could leverage to implement some of this networking behavior at the application level that we'll need. Envoy implements things like zone-aware routing. So if you're trying to load balance between on-prem or in the cloud or across multiple availability zones in the cloud, it has things like circuit breaking so that you don't flood your application and use up all of its resources because of some issues downstream or upstream. Outlier detection, things like if I'm making calls to a host and it's misbehaving, I can eject it from that load balancing pool. Traffic shadowing, so if I want to do a lower risk rollout or release of my service, I can deploy it and then take production traffic out of the critical path, shadow it over to my new release and see how it behaves, right? So we can do more controlled releases. Things like routing. So let's say I do want to take 1% of my live traffic and route it over to a new deployment. I can do that as well. Rate limiting, and I talked about some of the metrics collection. Since it knows the traffic that's going through it, it's able to report things like I said, number of requests going through, number of bytes going through, latency issues, circuit breaking events, and so on. It's also able to propagate headers, at least in HTTP, able to propagate headers, like request IDs, so that, and potentially even tracing headers, like open tracing headers or zip install headers. Can propagate that so that we can have and we can trace throughout the system what's happening with a request. Envoy can be used as an edge proxy. So at the outer limits of our cluster, as traffic is coming in, we can apply these features and get these benefits. We can also use Envoy as a proxy between services inside of our cluster. And in this model, we're sharing the proxy between a handful of different service instances. Now, I asked, well, putting a single proxy in the middle of our traffic flow is probably not a very good idea. Envoy can also be deployed as a shared or a service proxy, service instance proxy, that each instance of our service, each instance of our application actually has its own proxy. So we can configure the behavior of these different features per service, per instance. And so Envoy is, like I said originally, is written in C++, very high performant, very low tail latencies at the highest, once you get into the high throughput, and behaves predictably because of that. So if you looked at building a proxy like this inside of Java or some garbage collected language, you won't have that same certainty at those high performance numbers or those high tail latencies, P99. So we talk about running Envoy as one of these service proxies. Another word for that, at least in the container nomenclature, is if we want to run a couple of these containers together and collocate and deploy them together like that, first of all, of course, we're going to use Kubernetes. I think everybody's agreed that Kubernetes is the place where we're going to run our containers. But those get run as sidecars. So sidecar is another term for how we run some of these proxies collocated with our applications. Now, what this looks like is a little bit more scribbles. So what this looks like is Envoy runs next to the application. And in Kubernetes, this would be a pod. How many people use Kubernetes or are familiar with Kubernetes? Should be the whole room, but I'll take it. The application in this form is the downstream box. This is our, if we're doing Java, this is our Tomcat app or our Spring Boot app. And especially want to point out that it doesn't matter if this is a microservice or if this is a monolith or whatever. Like I said, this technology applies regardless of what's running in the container, regardless of the language and framework. So all of the traffic, when that application wants to make wants to communicate over the network to talk to another service, it will talk to Envoy. And Envoy manages the connection pools. It manages the tracking the number of failures. It retries. You can set your own retry policy and circuit breaking policy, timeout policy, deadlines, and retry budgets, and all this stuff can be applied inside of this proxy. And now from there, the traffic goes to the upstream services, which in a cluster could also have those proxies. They don't have to, but would be ideal if they all had those proxies. Then they all get the same behavior. Let me show you a super quick demo. Please cross your fingers for me, please, because these demos fail wildly and unpredictably at times. Let me make it a little bigger, maybe, so you can see it. Is that all right, kind of? All right. Now, this is a live demo. People are going to come up to me afterward and say, are you really typing that? No. But it is a live demo. I have it typing for me. So what we're doing is we're starting up if we come back to our slides real quick, we're starting up a sample service called HTTP bin. HTTPbin.org, if you go to it right now, you can see just when you call /get, you'll get back a response. If you call /headers, it'll show you the headers that you sent in. If you call /status/5 or whatever, it'll return that. So you can kind of control the behavior of the service just by calling it. So we started up one of those. Let's make sure that we can curl into it. And we're running all of these in Linux containers. And we see what we called /headers, and we got back the headers that we called it with. Nothing too special here. Now let's take a look at running Envoy. And I did Envoy/help, so you could see it's a binary. It's a C++ binary. We can pass in some parameters. Things like the config, so -c is config. Things like the zone that it might be running in, the node name, and so on. So we can bootstrap this binary by passing in some of these parameters. So if I try to start it up, and then it complains that I didn't pass a configuration into it, then maybe we should pass some configuration to it. Let's look at a config file. In Envoy, it's configured with a blob of JSON, and you can control things, like I said, what happens when the connection or a request comes in, what happens to its routing. Well, this is a simple demo. For any call that comes in, we're going to route it to this cluster, the HTTP bin service cluster. We also have a retry policy specified here. I don't know, does that get better? Yeah. So we also have a retry policy specified here. We can also specify circuit breaking and everything else. So this means if we have a 500 error, then Envoy will automatically retry for us 3 times. So let's bootstrap that up with the configuration file. Type all that stuff. And now the proxy should be running. Did it come up okay? We'll look at the logs. Okay, so the proxy came up. We have it configured to always send traffic to the HTTP bin service and retry on 500s. So let's curl the proxy. Let's do a curl /headers. What do we see? We see that it added a new header, the request ID. So this is a unique request ID as it comes into the proxy that can then be propagated throughout the cluster so you can track exactly what happened with this request. Let's get some stats about the proxy. So there's a whole pile of stats. All of the current, what's going on with the proxy right now is, we can see that. Let's filter some of that. It's a lot of stuff. Let's look at the retry stats. And we see, well, we don't have any retry events because we haven't had any failures. Let's force a failure. Let's call curl status 503. We should get some failures that came back. Let's check those stats again. The stats now show that we retried 3 times. And we retried because we were getting we were getting 500 errors. So we didn't change anything in the application code. We didn't add extra libraries and so on to implement timeouts and retries. We set a policy on this proxy that says, hey, when this happens, do this for me. Everyone got that? Any questions? Yes?
Does the request ID, does that mitigate using something like Jaeger?
No, it doesn't. And I'll build up to that. Yeah. So the question was, who would be responsible for maintaining these configuration files? And so it'll be both sides of the fence, right? You'll have some sane defaults that the operators want to have in place so that you don't, when you deploy something, you don't just blow everything up. But then the developers and the service owners would have the opportunity to override those and make more configuration changes. Does that make sense? Yes, there is. Let me keep moving, and then I'll come back to that toward the end. Okay. Now, so let's say we have these service proxies, these sidecars deployed along with our services. Who's heard the term service mesh, by the way? A lot of, a handful. Okay. At KubeCon, this was there's lots of talks, lots of buzz, lots of good stuff about the service mesh. Even our own Clayton Coleman, in his keynote, regarded 2018 as the year of the service mesh. But if we have these little proxies running around all over the place, what does that get us in terms of the cluster? How do we think about this as at a higher level than just tweaking some JSON files? So a service mesh, then, is the collection of these things, right? So it's the decentralized networking infrastructure that lives between the services, right? We talked a little earlier about the complexity showing up between the services. This is where the service mesh fits to provide resiliency, security, observability, and control, routing control. And a service mesh is comprised of these the data plane, these service proxies, these sidecars, and a control plane to make some sense of it in a fleet of machines and make some sense of it in terms of a cluster. All the traffic, then, would be flowing through the data plane, these proxies. And if we're able to, if all the traffic is going through that, we can control it, we can observe it, we can inject maybe failures in there to test, to stress the system. We have a lot more opportunities with it. Now, the only thing that that we keep in mind is that for centralized or for application networking infrastructure like this, we don't get too excited about trying to inject a ton of business logic into it, right? Whether it's API management or whether it's service mesh or whether it's integration, we have to be careful not to centralize that business logic. Meet Istio, Istio.io. This is an emerging implementation of service mesh, which includes Envoy as the default side proxy, service proxy, and the control plane for managing these proxies in a cluster. So deployed on Kubernetes, what this looks like is the control plane components, which I'll talk about in a sec, and the pods that are running with the service proxy inside the pod. Now, the control plane is made up of a component called the mixer, which we'll talk about in a sec, the pilot, and the CA, or Istio auth. The pilot is in charge of actually delivering those JSON configuration files to the proxies. And as a client, or as a user of this cluster, you would interact with the pilot through command line interface, through automatic injection of these proxies that could happen inside the cluster. As you spin up a new pod, Kubernetes can automatically inject these proxies, or probably more likely as a developer through CI/CD, being able to make deployments, make changes, and doing all that through CI/CD. Mixer is an intended to be a highly available component, 5 nines, according to Google. So Istio was sort of envisioned from Google, Lyft, and IBM. And since then, others like Red Hat have jumped in to embrace this. But so the mixer is envisioned to be a highly available component that is used for access control and quota checking and policy enforcement and metrics collection. Provides a single uniform API for syndicating some of this telemetry data back to backend. So you can have plugins for the mixer, things like distributed tracing, like Jaeger or Zipkin, or API management tooling, or metrics collections like Prometheus, and so on. And so as traffic is flowing, the pods, these data proxies are checking with the mixer, saying, hey, is this call allowed? Is there a policy that allows or disallows this particular call? And then the last component is the Istio CA, which manages certificate signing requests and certificate delivery to the pods, that allows us now to implement. So we can do all these things at the data layer. One thing I left out was we can actually secure the communication channels now. Since we own the control points for how the connections are made, we can do things like mutual TLS in between the systems. And Istio CA, especially running in Kubernetes, in conjunction, assigns identity to the workloads and can issue certificates and rotate those certificates or revoke those certificates to allow mutual authentication to happen transparently. The applications now, as a Java developer, I don't know how many times I've spent hours and days wasted digging around in Keystore and TrustStore and trying to get all that crap to work, right? So Istio looks like this. Istio is the control plane. The service mesh is the overall control plane and data plane here. What are some of the higher order cluster semantics then? I alluded to that. The observability. Now, so now we can build, somebody asked about Jaeger, we can build the request ID and propagate the XB3 headers for open tracing. Now the applications have to help out to make sure that those specific headers get propagated, but that's such a thin layer of intrusion on the application. So the service mesh can then, as these headers are being propagated throughout the service, do distributed tracing for you. The service mesh can send these spans to Jaeger, to the open tracing systems, and do that stuff for you. We are able to get gradual deployments and releases. Policy enforcement happens at the mixer, and the plugins that you can plug in for your own more detailed policy enforcement. The reliability aspects, retries, timeout, circuit breakers, that kind of stuff. And chaos testing. It's one thing that is quite important. You cannot reliably recreate production in QA. I think we all know that. But so when things get into production, we want to observe them. We want to have very low risk deployment, so we want to be able to control the traffic to be able to do that. But we also want to inject some failures into there and see how the system responds using observability metrics, logging, that kind of stuff. So Istio allows us to do that. I have a much more in-depth workshop that goes into each one of these components. Take a look at that as you will. There's going to be a lot of good content coming out at DevNexus. Look at what the Red Hat developers are going to be doing around Istio and workshops at DevNexus. That's the one here in Atlanta, right? Yeah. OK, so the demo that I'm going to try to pull off here is how do we do, what does the tracing stuff look like? What does routing look like? And if we have time, try to get to the circuit breaking stuff. Sound good? And I'll post these slides. Reach out to me. I've had people come up afterward and say, hey, can I reach out to you? I was like, yeah, that's why I put this stuff up here. Reach out to me if you have any questions or if you have any comments. Get involved in the Istio community, Envoy community. The slides, I put all my slides for all my talks on SlideShare. This talk is already on there. And then some of the follow-up links. But let me get to the demo. All right, let's try that again. Again, live demo. We're going to look at the HTTP bin service, right? So we saw that in the previous demo. What we're going to do is deploy this onto Kubernetes. And if you're using Kubernetes, you're of course going to be using OpenShift. That's the enterprise-ready Kubernetes. Now, so here's the deployment descriptor for the HTTP bin service. You'll notice it has HTTP bin, all the proper Linux container images and so on, but it doesn't have the Istio sidecar proxy. It doesn't have the service proxy in it. So what we want to do is inject that proxy. Now, I'm using, this is why I need your help crossing fingers. I'm using the latest master from Istio, so the command line looks a little bit longer than it really needs to be. But what we see here is we see our HTTP bin container. Maybe it's farther down, but right down here. We see the container right here, but then we also see a proxy injected here. This is the service proxy. This is Envoy that I showed you earlier. And a bunch of the parameters that we need to pass into Envoy to make it start up, pointing at things like the pilot from where it's going to get its configuration. Okay? So now, I was just showing you, I did the kube inject. I didn't actually install it. I didn't actually deploy it. So let's do the deployment right now. We're going to create it by doing this injection. You can see it, right? Right, we're doing the injection of our HTTP bin v1 Kubernetes resource. So everything was created, hopefully. Let's get the pods, everything's running. Now, one thing to notice is we're ready 2 out of 2. We have our HTTP bin service and the service proxy running in this pod. If you're unfamiliar with Kubernetes, Kubernetes can atomically deploy an application that's made up of multiple containers. It can say your application plus another Docker container, another Linux container can be co-deployed as a single deployment. That's what it's called a pod. So we have 2 out of 2 running. No, that's not what I was expecting. Let's try that again, just real quick. All right, we got that, we got that. Create the service. It'll complain because it's already created. All right, and then get the pods. That's fine. Control C out of it to get to, all right. Can we query the HTTP bin service? We're gonna log into Kubernetes, into the cluster, and we're gonna do a curl. Now, when we curl this, notice all the traffic for HTTP bin service is now going to be going through the proxies. All the outbound from HTTP bin and all the inbound to HTTP bin is going to be going through the Istio service proxy, Envoy. And you can see it added some of these headers. And these headers would be used in a distributed tracing, an open tracing environment to do distributed tracing. Now, on the bottom left-hand side, pane down here, we're watching the logs of our HTTP bin service. On the top pane, I just created a new pod which deploys a load balancing tool or load generation tool injected with our proxy. Okay, so here we should have 2 pods. Let's see. We got 2 pods. They're both running. Both of them have the sidecars injected. Now let's query our HTTP bin service with the load generation tool. We're going to call it 5 times, and we should see at the bottom it generated some load. You can see through the logs that it generated some load. And up here we can see that 5%, and we got response code 200. So that's all good. Now let's create a version 2 of our HTTP bin service. So we could say this is a new deployment. Maybe we have some code changes or whatever, and we want to deploy it into production. We want to bring it into production. But we don't want it to start taking traffic, right? In Kubernetes, if you label the pods in a certain way that they match a Kubernetes service, I know that if you're not familiar with Kubernetes, this might just be gibberish, but when you start, oh no, please don't fail. Okay. When we start calling into the HTTP bin service, it really is just going to load balance across both of them, because there's no routing, there's no higher level routing constructs in Kubernetes per se. In OpenShift there is actually at the ingress level, but inside the cluster there's not. We can see there were 40 calls, and they were load balanced. It looks like they were load balanced across version 1, version 2. But we don't want that, right? We want to route all traffic coming into the cluster to V1, version 1 of our HTTP bin service. We don't want people to see version 2. So in Istio, we can define route rules that basically say, if you're trying to talk to HTTP bin, always route to version 1, and this being the default rule. That make sense? So let's create that. Let's apply our rule. No, HTTP bin is a HTTP bin service .org. So no. Well, so it is, as we've deployed it, is a deployment inside of Kubernetes, and also has a Kubernetes service. Yes. Right. So we've created our route. Now, if we execute load against that, again, HTTP bin service, we shouldn't see any of it go to version 2. Right. This is what we expect. Our version 2 is deployed into production potentially. Right? So that is kind of what we did. It's deployed, but it's not released. It doesn't actually have traffic coming to it. Now, let's say we do want to, for maybe internal users, we do want people to see the new version, and we want to get feedback from it and want to see how it behaves. Let's say we want to dark launch it. Only requests with the, let's come back to that. What the hell did I do? Only requests with the headers x dark launch equals v2 should go to version 2. Right? So this is a route rule that we're going to create that says if your traffic has this particular header, then you can route it to version 2. And this is not just at the ingress. This could be nested deeply into the cluster. So let's create that route rule. All right. Now let's query our HTTP bin service. We're not going to set any headers. All load should go still to version 1, which it did. Now let's set a header x dark launch, and we see that traffic went to version 2. Any questions about that? No. So yes. So the API gateway so Istio, the service mesh and API gateways do have a lot of potential synergies. Whereas the API gateway is typically implemented as a centralized proxy for north-south traffic, incoming traffic. You get some of the routing capabilities at that point, right? But as the traffic comes in and starts to propagate throughout the rest of the cluster, we need that type of control, routing control, as it propagates as well. Exactly. Exactly. Well, so API gateways is an implementation of a proxy. API management is a totally different thing than service mesh. API management is something where you would allow developers to go register APIs and write documentation and create plans and policies and rate limiting and all that. But some of the rate limiting aspects do cross over into what the service mesh can do. Now, what you could look at is how the API management tools could specify the policies that then the service mesh enforces.
So is this lighter weight form then?
Yeah, so in this scenario where we're looking, the proxies are actually running with the applications, right? And so you can get things like TLS termination at the application, not at some central gateway, and then somehow you have to figure out how to get it back to the application, right? The other downside to having centralized gateways at the ingress is great. Pools of proxies at the ingress is awesome, but internally, as you start to contend with different types of workloads, noisy neighbor problems, how you configure a particular service differently from another service, you'll want that decentralization. Yep. Say again? The question is, how do we shift from version 1 to version 2? Yeah. Yep. Traffic is coming in. It's coming in at the ingress. And with Istio, you can specify routing rules like we did here that say, well, OK, I want to shift traffic from, but only 1% of the traffic, let's say. Right? And we'll gradually do it. We'll say, do 1%. We'll keep an eye on it. Do we get any errors? Are people seeing latency spike? And so on, right? Then we might want to do 10%. Or we might not, we might want to say only 10% of the traffic where the user is a non-paying customer do we want. So you can get pretty complicated with how you specify the groups or I forgot the name of the word, but how you specify the cohorts that belong to a certain version of the service. Yep. Time. Potentially a plugin, potentially an A/B style service that you implement that because in that case you're probably going to want more business-oriented logic to specify what those cohorts are and how they are. All right, so I'm getting we're done. I'll be around here all day. I'll be here at happy hour. Come get a drink. Thank you guys for listening. Thank you for your questions. I'll be happy to answer more afterward. Thank you.